Hi, in this video I'm going to continue on industrial chemistry, and today we will start with the catalysis in industrial process. Now again, catalyst definition, refresh your memory. Now you know that for industrial process we want to have the reaction proceeding as fast as possible in a safe way. And one way to achieve that is to use catalysis, or we add catalyst into our reaction chamber so that the reaction can proceed faster. So here we want to talk more about the catalyst, especially their application in industry. Now first of all, we have two types of catalyst. We have positive catalyst and negative catalyst. And positive catalyst can speed up a reaction. A negative catalyst slows down a reaction. Or sometimes we call it inhibitor, right? But very often, when we talk about catalyst, we are talking about positive catalyst. Okay? Now, these are some features about catalyst. You can read it yourself. Now, down here, like I said, catalysis is important because it can speed up the manufacturing process, and also because the catalyst is able to speed up the reaction, so we don't have to use extreme conditions. Because without the catalyst, if we want the reaction to be fast, all we can do is to increase the temperature or increase the pressure. But increasing both the temperature and pressure means we are using extreme conditions. And operating reactions under extreme conditions are both costly as well as dangerous. But that's why using catalysts can avoid the use of such extreme conditions. Okay? Now, down here, we have some examples of industrial process that are catalyzed. For example, Haber process. In the later part of today's video, we will break down the details of Haber process. This process is used to make ammonia, and the catalyst we use is iron. Okay. The second one here, fermentation, basically to produce ethanol from biomasses or like crops. You see, the main reaction involved is having this glucose, which is a simple sugar, break it down into ethanol and carbon dioxide, and this is catalyzed by an enzyme in yeast. Okay. Now down here, contact process. Contact process is out of the syllabus, but this process was in the syllabus in certificate level, and this process is used to make sulfuric acid. Okay. And this reaction is catalyzed by vanadium 5 oxide. Okay? Now down here, it is a laboratory experiment showing you the fermentation. Very simple setup. We have sugar solution, right? Over here, sugar solution, and yeast. And yeast is a microorganism, and inside this yeast, they have this enzyme, catalyst. Okay? And the reaction is taking place at a mild condition, 35 degrees Celsius. The reaction takes place, the glucose is broken down into ethanol and carbon dioxide. Ethanol is miscible with the water inside. However, the carbon dioxide will be able to collect it in this test tube, and the carbon dioxide will turn lime water milky. Okay? On the right hand side here, we try to compare two types of catalysts. Here we have inorganic catalyst and biological catalyst. Basically, inorganic catalyst corresponds to some transition metals or some transitional metal compounds. For example, just now with our three examples here, iron and vanadium 5 oxides are considered as inorganic catalysts. On the other hand, biological catalyst is referring to enzymes. So biological catalysts are made by cells, made by microorganisms, or made by organisms. Okay? So when we try to compare these two types of catalysts, we say that inorganic catalysts are less specific in action, whereas enzymes are highly specific. Specific means whether or not it catalyzes one reaction only. So if it has a high specificity, that means the catalyst will only catalyze one reaction only. Whereas a low specificity means that the catalyst is able to catalyze more than one reaction. Okay? Now, the advantage of being highly specific is that the catalyst will speed up only one reaction, and therefore it will less likely leading to side reactions, leading to side products. Okay? Now, down here, what about their operating conditions? For inorganic catalysts, it can occupy at high temperature, high pressure. It can also be occupied at low temperature, low pressure. So it has a higher tolerance to extreme conditions. Whereas for biological catalysts, it can only operate at mild condition. This is because enzyme is protein in nature. Having extreme condition will damage, or we call it denature, the enzyme, and therefore making it malfunction. Therefore, mild conditions are used. Also, enzyme is often dissolved in water with a moderate temperature and pH. Okay? For inorganic catalysts, it could be organic solvent, it could be water, right? And it can also be used at extreme conditions. Okay? Down here, there are some examples. You can have a look at these. Now, here we have a term called catalyst poisoning. So often we say a catalyst is poisoned. Now, poison, we only talk about poison when we talk about animals, living things, right? However, when we talk about a catalyst being poisoned, it actually means that the catalyst has lost its function. Now, for example, remember we have a device called catalytic converter installed in car exhaust system. And inside that catalytic converter, we have either platinum or rhodium. Okay? And these metals, they provide a surface where the exhaust gas can adsorb onto the surface. Now, adsorb basically means it is attached on the surface, but it is not tightly bonded by whatever ionic bond or covalent bond. They simply get attracted to the surface, okay? And by doing this, it can bring the gas from a three-dimensional space to a two-dimensional space, right? On the surface, which can allow the exhaust gas to react with each other easier, okay? And therefore speeding up the reaction. However, there are some impurities, which is also known as the poison molecules, and they will be adsorbed very, very strongly onto the surface, okay? Or even some situation they are bonded to the catalyst. This way, it will reduce the surface area available for the catalyst to adsorb other exhaust gas, and therefore reducing the catalytic efficiency and later on render it malfunction. Okay? So this is what we call catalyst poisoning, right? Now, next part, industrial process. So here, that would be another main content for industrial chemistry, because we are going to look into details of three important industrial processes. We have Haber process, chlor-alkali industry, and also methanol industry. Okay? We will break it down to you one by one later. But first of all, let's do some brief introduction about industrial process and be familiar with some terms. Now, first of all, if you look at this diagram, so they summarize the chemical process in industry. Basically, we must have raw materials, and very often we need water as a solvent or for cleaning, and also we need energy, of course. So all of this are used to prepare feedstocks. Now, what is feedstocks? Now, you can have a look at the definition here about the feedstock. Now, feedstocks are reactants that goes into a chemical production process directly. Okay, and feedstocks are prepared from raw material. So, what is the difference between feedstock and raw material? Basically, feedstocks are modified or purified raw materials. Now, you can look at these examples, then you are able to tell easily. For example, if you want to make a plastic bag, and plastic bag is often made by polyethylene, then the raw material will be petroleum or the crude oil. Okay, and the feedstock will be ethene. You can tell ethene is the immediate reactant that is used to make polyethylene, isn't it? So this one is what we call the feedstock. Ethene, however, is not directly extracted from the surrounding, from the nature. Instead, we extract the crude oil or we extract the petroleum, and then we process the petroleum by fractional distillation, by cracking, and then by another fractional distillation, and then we can collect the ethene. All right. So this kind of tells you the difference between raw material and feedstock. Okay, another example will be here, chlorine bleach, which is essentially having the active ingredient NaOCl. Now NaOCl can be prepared by reacting chlorine with sodium hydroxide. But where does chlorine and sodium hydroxide come from? Well, they come from the electrolysis of seawater. So seawater will be the raw material. These will be the feedstock. Okay. All right. So now you know the difference between raw material and feedstock. Okay. So after the feedstock has been prepared, they are loaded into a chemical reactor, and inside the chemical reactor, very often we have a catalyst to speed up the reaction. So as the reaction proceeds, most of the industrial process release heat. Okay, so the reaction chamber will become hotter and hotter. So there must be some energy change or energy flow between the cooling system and the reaction chamber. Okay, so we will talk about one example of how it actually works when we talk about Haber process. Okay, but all you need to know is that the reaction chamber is where the reaction takes place. Catalyst will be present, and there is also cooling system or any energy system to make sure that the temperature is monitored. Okay. Also, very often these reactions are reversible, or simply the reaction is not fast enough to consume all the reactants. So after the product passes out from the reaction chamber, there may be some unreacted reagents. Very often we want to also collect these unreacted reagents, so we will recycle them and pump it back to the reaction chamber. Okay. Now, the product that we have, of course, will be separated from the catalyst or byproduct or impurity solvent, and also they will be purified, and at the end of the day, we will have product. Of course, we will also have byproduct, which may be useful because byproducts could be further processed to make something useful, and also there may be some waste that we have to treat it. Okay, so these are the whole story, a general story of a chemical process in industry. Okay. Now for chemical process, we have two mode of working. We can have batch processing, we can have continuous processing. Just give you two examples. For example, if you talk about wine, red wine. So you know red wine is made by grapes, right? So every year we have one harvest of grapes, right? So basically we harvest the grapes and then we make a batch of wine, and then we wait until another perhaps autumn or winter where we have another harvest of grape, and then we make another batch of red wine. Okay, so this mode of production is called batch processing. Okay, so the manufacturing process is not continuous; it's discontinuous. Okay, batch by batch. Now, however, most of the industrial process adopt continuous processing. Okay, so we said that the feedstocks are fed into one end of the reactor, and product is withdrawn at another end of the chamber, so it forms a continuous flow. Okay, continuous processing, of course, have the highest production rate, the highest efficiency, basically 24-hour non-stops. Okay, well, of course, it depends on the nature of the reaction. Like for wine fermentation, you can't have continuous processing, right? It's because it depends on the harvest of the grapes, right? So, of course, this simply tells you that we have two ways of processing our feedstocks. Now down here, just to show you some categories of products that is made from industrial process. Of course, there are more of them, but these just give you some general categories. Okay. Now, just now, the two parts, the catalysis in industry, also the introduction to industrial process, to be honest, not very important. So that's why you may notice that I quickly go through it. Now, this part is very important, Haber process. Almost every year, this topic will be asked, Haber process. Whenever we want to study an industrial process, we need to know the feedstock, the reaction, and the reaction condition. And all of these you need to memorize it. Okay? The reaction, perhaps we look at the reaction first. We have N2 reacts with H2, reversibly forming ammonia. Okay? Notice that we use iron as the catalyst, and of course we need high temperature. The reaction is exothermic. Okay, you need to bear in mind the forward reaction is exothermic. But the reaction conditions, you see 400 to 450 degrees Celsius. If the question asks you about the condition, you can simply put down 400 degrees Celsius or 450 degrees Celsius. 200 atm, you need to memorize this. Okay, let me underline for you. And also we use iron catalyst. Okay. N2H2, where are they come from? Now N2, of course, is coming from the atmosphere, and N2 coming from the atmosphere. And my question is, in which industrial process do we obtain pure nitrogen? Do you remember? The process is called fractional distillation. Of liquid air. Okay? Do you remember this? You have learned it in Form 3. Okay? Now for hydrogen, remember hydrogen does not present in air. So hydrogen, they are usually come from a process called steam reforming of natural gas. Steam reforming of natural gas. Now, what are natural gas? Well, natural gas are one of the fossil fuels, and they contain mainly C1 to C4 hydrocarbon, and among which most of them are methane. Okay, so we get the methane, and judging from the name steam reforming, you can tell we react with steam. Okay, and this will produce carbon monoxide and hydrogen gas. Okay, now you see this reaction is able to produce huge amount of hydrogen gas, and this hydrogen gas can be used in Haber process. Okay, the condition required is much harsher. Okay, it is over 700 degrees Celsius, 30 atm, nickel oxide catalyst. Okay. Now down here, this diagram outlines the actual industrial process of Haber process. Now this is very important. You need to know the process. You also need to know why or what are the purpose of each step. And you also have to appreciate the design. Okay, explain the purpose of such a design. Okay. Now first of all, we have the feedstock made in 1:3 ratio. This is basically following the stoichiometry of the main reaction. Okay, 1:3 ratio, and they will first add it into a purifier to remove carbon monoxide, carbon dioxide, or water vapor. Okay, we always purify our feedstock before loading it into the reaction chamber. Now, before we load it into the reaction chamber, we will actually add it into the places called heat exchanger. Heat exchanger. Now, at this moment, a heat exchanger, all you need to know is that it is able to heat up the cold feedstock. Heat up the cold feedstock, because remember, the reaction requires high temperature to proceed. Okay, so the reaction chamber is operating at 400 degrees Celsius. Of course, we need to first heat up our feedstock before we load it into the reaction chamber. Otherwise, the chamber will be cooled down by the cold feedstock. Okay, so the feedstock will be heated up before loading it into the reaction chamber. So the hot N2 and H2 mixture is loaded into the chamber. Reaction takes place to produce ammonia. Okay. Now, here, after this, then this hot N2, H2, and ammonia. So we have the product, we have the unreacted reagent. You can put down here. This is the product, and these are unreacted reagents. They will then again pass to the heat exchanger again. Now, why do we have to pass it down the heat exchanger? It's because we want to cool down the product mixture. And how do we cool down the product mixture? Well, remember at the beginning we have this cold reactant, the cold feedstock, right? So what we're going to do is we pass the hot product mixture to the reaction mixture, which is cold. In this case, the heat from the hot reaction mixture can be transferred to the cold feedstock. In this way, not only can we cool down the mixture, but we'll also heat up the feedstock, and this way we can better utilize the heat energy. Okay? If we have separate chamber, one for heating up the reaction feedstock, another one for cooling down the product mixture, then it will be a waste of money and inefficient. So this heat exchanger allows us to transfer the heat from the product mixture to the feedstock. Okay? Now, of course, the two mixtures are not directly mixed together. Of course, they use pipelines to make close contact with one another, so it facilitates the heat transfer by conduction convection. Okay? Now, after the heat is transferred to the feedstock, then we have a less hot product mixture. That makes sense? And this less hot product mixture will pass down to an ammonia condenser. As you can tell, this part is used to condense the ammonia and change it back to liquid. Okay? Now, remember, the boiling point of ammonia is much higher than N2 and H2. Ammonia, of course, they have hydrogen bond between molecules, whereas N2 H2 only weak van der Waals force. So with a much higher boiling point of NH3, that means it is easier to condense it back to liquid. So this less hot gaseous mixture, after directed to the ammonia condenser, then the ammonia will be condensed, whereas the unreacted N2H2 still remain as a gas, will then pump back to this part where it is recycled back and mixed it with a cold feedstock. Again, they will both be directed into the heat exchanger, get heated up, and then again directed to the reaction chamber for further reaction. So this way we can prevent the waste of reactant. And also there is one more importance for ammonia condenser. As we keep removing the product ammonia, the equilibrium will always favor the product side. So this one will favor a higher yield of ammonia. Okay? So this continuous removing of ammonia is another strategy to increase the yield of the product. Okay? Now all these remarks, basically I have discussed it, so have a quick look. First of all, this purifier removes contaminants which may otherwise poison the catalyst. A heat exchanger. Now this one is important. I want you to highlight this one because the past paper may ask you to describe the purpose of heat exchanger. So here, the heat exchanger allows the hot products to transfer the heat to the feedstock. So it can save energy by both heating up the feedstock and cooling down the product. So it's a very clever design. And down here, ammonia has a much higher boiling point. Again, something important here. Ammonia has a much higher boiling point. Therefore, it can be separated by condensation. Okay. Also, since the reaction is reversible, any unreacted reagent will be recycled to reduce wastage and also boost the percentage yield. Okay? So these are all the important things about the Haber process that you need to know. Okay? Now, on the right hand side here, we want to discuss some industrial condition and also compromises. Actually, we did talk about this when we talk about equilibrium. Like I said, we do not have the best, perfect set of conditions. Okay, there's always contradiction between four factors: the rate of reaction, the yield, the cost, as well as safety. Okay, there's always contradiction among these four factors. But that's why we need to make compromises. We want to set up an optimum condition so that all four factors are reasonably satisfied. Okay, so here, when we're operating the reaction at a very high pressure, the good thing is it can speed up the reaction because there are more collision. Also greater yield because if you look at the reaction here, okay, there are more moles of gaseous substance on the reactant side than the product side. If we increase the pressure, the equilibrium will shift to the right hand side and therefore increasing the yield of ammonia. But that's why this is another advantage. So faster reaction, greater yield. However, the drawback is maintaining high pressure is costly and dangerous. Now, operating it at high temperature will of course speed up the reaction. Okay? However, it will lead to lower yield because again, you remember the Haber process is exothermic. By increasing the temperature, it will actually make the equilibrium shift to the left, performing more endothermic reaction. So this one will obviously lower the yield. Ion catalyst, the advantage is it will speed up the reaction. So actually, here I would rather cross it out. Okay. Now also one more remark here. Usually this ion catalysts, they are made into finely divided ion. Okay? So this finely divided ion is of course to increase the surface area of contact. Therefore, increase the catalytic efficiency. Okay? Alright, now down here application, like why do we have to perform Haber process to make ammonia? Because ammonia can be used to make chemical fertilizer, can be used to make nitric acid, can be converted into other nitrogenous compound. Also, it is an active ingredient in window cleaner. Okay? So it's a very useful industrial product. Okay? Now down here we have something called Ostwald process. Basically, it is showing you the steps to produce nitric acid from ammonia. Okay? Now, the reaction takes place in 3 stages. The feedstock is ammonia and also oxygen. Okay, ammonia and oxygen. Okay? Now, ammonia is coming from Haber process. Oxygen, again, is coming from the fractional distillation of liquefied air. Okay? Now, in stage 1, ammonia reacts with oxygen to form nitrogen monoxide and H2O. And then, nitrogen monoxide is oxidized into nitrogen dioxide, and then further oxidized to form nitric acid. Okay? Now, these reactions, you must know how to write balanced equations. In DSC, they will very often ask you about the oxidation state. Okay? Now, notice that here, in the first stage, ammonia is in -3 oxidation state. Okay? So it is pretty much reduced. But with the oxidation of O2, it becomes +2 here. So there is a huge increase in oxidation number. Okay? And after that, we have basically stepwise oxidation of nitrogen. So here, nitrogen is oxidized. Here, oxygen again oxidized. and here to here. So you see the oxidation number keep increasing from -3 at the end, +5. Okay, so that's why you see every single step requires oxygen. Okay, oxygen is definitely the oxidizing agent. Okay, so here oxidation number of N keeps increasing in each stage. Okay. Now down here, it is talking about the manufacture of nitrogenous fertilizer. So we have two types of nitrogenous fertilizer: ammonium sulfate, ammonium nitrate. So you can tell the ammonium part is coming from ammonia. The nitrate sulfate is coming from the corresponding acid. It's just like the preparation of soluble salt, right? So you see, with hydrogen and nitrogen being the feedstock, it produces ammonia, and ammonia can be used to make nitric acid by the Ostwald process, and ammonia combining with the nitric acid to form ammonium nitrate. Ammonia can also react with sulfuric acid, which is made from contact process, and to form ammonium sulfate. Okay. All right. So that's it for the Haber process. Now we have some practice question. So can you pause the video, attempt this question, and then resume the video and check the answers. Okay, let's have a look. Chemical reaction, Haber process. N2, H2, reversible sign, NH3. What catalyst? Iron. Briefly explain the function of heat exchanger. Okay, so heat exchanger, it allows
the heat from hot powder mixture to be transferred to the cold feedstock. So it saves energy in both cooling down the product mixture and heating up the feedstock.
Okay. Now down here, how is the product being separated from the unreacted feedstock? So the product here is ammonia, the unreacted feedstock. So here ammonia, the unreacted feedstock is N2 and H2. So how are they being separated? Well, by condensation. By condensing ammonia, okay, in ammonia condenser. Okay. Now, what is the fate of the unreacted feedstock? The fate. That means, what are we going to do with the unreacted feedstock? Well, they are recycled.
Back, okay, to the heat exchanger. Okay, get heated up and directed back to the reaction chamber.
Okay. I suggest one way to increase the yield and state how this modification may compromise the manufacturing process or industry. So one way to increase the yield, you can talk about pressure increase, okay, or temperature decrease. But pressure increase, of course, it will be costly, okay, to maintain high temperature, high pressure. Or you can say temperature decrease. However, okay, the reaction rate decrease. Okay. Now, state two reason why ammonia produced it must be carefully stored. Okay. Now, so if you look at carefully stored, it has to do with the hazardous nature. So ammonia is what? It's an irritating gas. Now, also, it dissolves
in water to form alkaline solution, which is corrosive.
Okay, so these are some hazardous nature of ammonia. Okay? So here we are talking about how ammonia is reacted to form nitric acid. So state the oxidation number of N in ammonia and nitric acid. So here it is -3, here it is +5. Write down chemical equations of the three reactions. Basically, you can refer back to the note. You have ammonia, is it? Okay, so down here, nitric acid reacts with ammonia to form ammonium nitrate, which is a key compound in chemical fertilizer. So just one reason why farmers use ammonium nitrate instead of ammonia to increase the nitrogen content in soil. Well, of course, you can think about it from two ways. First of all, the convenience, and secondly, the safety aspect. Now you know ammonia nitrate is a solid, whereas ammonia is a gas. So
Ammonia nitrate is a solid, while ammonia is a gas. So it's more convenient for transport
and use. Okay. Also, you can talk about
ammonia is an irritating gas, while ammonium nitrate is harmless.
okay. Another key compound in chemical fertilizer is ammonium sulfate. Compare the nitrogen content of ammonium nitrate and ammonium sulfate. Show your workings. So for nitrogen content, we have to compare the percentage by mass of nitrogen. So here,
Percentage by mass of N in NH4NO3. So we have 14 times 2 over 14 times 2, 4 plus 16 times 3, okay? Times 100%. So if you type the calculator, you have 28 divided by 14 times 2 plus 4 plus 16 times 3. So that would be 35%. So you do something similar. So we have, again, 14 times 2, and down here we have 14 times 2 plus 4 plus 32.1 plus 14 times 4 times 100%. So we have 28 divided by 14 times 2 plus 4 plus 32.1 plus 16 times 4, and that would be 21.9%. Okay? So obviously, the nitrogen content of ammonia nitrate
is higher. Okay? So that's it for today's video.